This example is the hydrolysis of a salt. And so in the first question, it asks us to write the net ionic. So what I'm going to do is write down the salt. So sodium with this weird propitiate ion. And then I'm going to, hydrolysis means add water. So I'm going to add HOH and just do a double replacement reaction. So what happens is I get some sodium hydroxide, so the Na and the OH get together, and then we form the acid. And so if we want to name it, so it's a propionate, so it'd be propionic acid, not one that's all that common. So that's the reaction, but the net ionic, remember that group 1s are pretty much figments of our imagination, and we know that that's a strong base, so that's going to be gone. But the end of this is not a strong acid, so we don't cross anything out from there. So that would be the net ionic. You would just not include the NAs and make sure that you put the charges in. So, and it's a weak reaction, so we are going to have a double arrow. The equilibrium expression then would just be that Kb, since it's an OH, is going to equal OH minus times the acid, conjugate acid, concentration, divided by the original salt concentration, which actually is a basic salt ion. And that's going to, we already got it equal to Kb. So now to calculate the Kb value. So in this particular case, I am given a Ka value. So it tells me the Ka is 1.34 times 10 to the minus 5. So the Kb value, or the hydrate value, is just 10 to the negative 14 divided by the Ka value, because this is the conjugate acid. This is the base. So I need the base K. I know that Ka times Kb is equal to 10 to the negative 14. So if I know the Ka, so the Ka is 1.34 times 10 to the minus 5. So then the Kb then would equal, if I work this out, and I know I have it worked out here somewhere, 7.46 times 10 to the minus 10. That kind of gave you a minute to go ahead and try and calculate it. So that's equal to Kb. So then when we look at the, now it wants to know what is the concentrations of each thing. And so there's a little tricky one in there, and that's the Na plus concentration. Well, remember, we crossed those out. So that means that they didn't change. And so if I look back at the top, I see that I have a 0.45 molar solution. So that's going to be my concentration of the Na plus. That's not going to change. But the OH minus and the propionic acid is going to change. And so I'm going to use just pretty much a rice, but remembering that we can just do the x squared over initial is equal to Kb, remembering that we are looking for a base, and so the OH and the propionic acid are both going to be x. So I just need to solve for x. So if I plug this in, I have 0.45 molar x. We solved for Kb earlier, x squared, the 7.46 times 10 to the minus 10. So algebraically, if I multiply both sides by the 0.45 and take the square root, that's going to give me these concentrations. And so when I work this out, I get that OH and the propionic acid are both 1.83 times 10 to the minus 5. So 83 times 10 to the minus 5 molar, do not forget your molarity, and that's going to equal to your OH minus concentration as well as your acid, conjugate acid concentration. So that's that question. And so then very easily it wants the pH of the solution. Well, that's the easiest part of all this, because I know that my OH concentration is 1.83 times 10 to the minus 5 molar. And then if we kind of just jump on our little conversions, we're down here on OH, and I want to get to POH. And so what do we have to do? We have to minus log. So if we minus log this number, so if I minus log, that's going to get me the POH. So if I minus log that value, I get 4.74. Well, that's not my pH value, that's my POH value. And so we know, kind of working on our little conversions here, that 14 minus whichever P that I know gives me the other P. So in this case, 14 minus 4.74 is going to give me my pH value, which is 9.26. And just a quick little reality check, is that a basic pH? And it is. Anything above 7 is a basic pH, and so that's a reasonable pH for this particular salt. So now I want to do one that's an acidic salt. So just quickly, this one, it wants us to calculate the pH of a 0.2 molar solution of ammonium chloride, and it gives me the Kb. So it's kind of a little instant thing. So let's first of all, just for fun, let's write the hydrolysis reaction. I know you like doing those things just for fun. So if I write this reaction, again, double replace, the base that this came from is ammonium hydroxide, or you could actually just write NH3. And the acid that it comes from is hydrochloric acid. Or we're going to find in just a minute that we could just write H+, because we're going to get rid of the chlorines. The chlorines are going to be gone because it's a strong, and so the actual reaction is just this, that NH4 plus comes from NH3 plus H plus, or you could have written NH4 plus HOH yields NH4OH plus H plus. Either one of those reactions will be your net ionic. So again, if we look at NH3 times NH plus over the ammonium ion, that needs to equal a Ka, because I have an H plus. That means I've got acid. So this kind of indicates that this is an acid. Well, I have a Kb of the conjugate. So this is the Kb. So again, Ka times Kb, acid conjugate base, is equal to 10 to the negative 14. So if I take 10 to the negative 14 and divide it by my Kb, 1.8 times 10 to the minus 5, that's going to give me the Ka that I need. And so a quick, simple calculation, that's 5.6 times 10 to the minus 10. And so if I plug in then, NH3 and H plus are both going to be my x's, so this is x and x, so I get x squared. My initial, remember, is going to be 0.2 minus x, but we're assuming that that molarity, that x, is going to be very small, and obviously if I have a 5.6 times 10 to the minus 10, it is going to be very small. So I'm going to multiply by 0.2, I'm going to take the square root, and I'm going to solve for x, which gives me my H plus. So when I solve for x, I get 1.05. Again, giving you a chance to calculate that. 1.05 times 10 to the minus 5. Molarity is my H plus. So we know the drill. I minus log that. That's going to give me the P. So I'm going to minus log this. So if I minus log that number, I get 4.98. Another little reality check. What is my x? Oh, my x is H, so I'm good. That is pH. And then is that a reasonable pH for something that is acidic? And 4.98 is below 7, so it is a reasonable pH. Remember, if it's not, then the pH would probably be 7 because it's just been watered down. So that's how we do hydrolysis of salts.